We are going to have a look at electric circuit. This is a circle. Now this one is a circuit. The word circuit comes from the word circle. Now, if you move from here in the circumference, you come back here. The charges will also flow in the circuit from there to there, provided the switch is closed. That's a switch there. And that's a bulb there. It's an emitter here. And that's a resistor here. And then there's a source of energy up there. Two cells make up a battery. So we have two cells there. Let's say two cells connected in series. Two cells connected in series there. If each cell is 1.5, we expect the combination to give us 3 volts. And then we will have a meter here called a voltmeter. The voltmeter will measure the battery there. Let's say 2 cells make up a battery. There's a voltmeter there. And this one, the emitter measures the current. This one measures the current. Now, in this circuit, the switch is open, which means electrons cannot flow or charges cannot flow in that circuit. Now what happens is, if you measure here, V will measure 3 volts, and this is called the EMF. Why? The battery itself has its own internal resistance. The battery has its own internal resistance. The battery has its own internal resistance. But because there is no current that flows through the battery, the voltmeter will measure the EMF. Now let's take a very circuit. Let's take the very circuit. And see what happens. See what happens. Yeah. Yeah. You still have your battery there. Still have your emitter there. Your bulb there. You still have a switch there, but this time the switch is closed. And you still have your resistor up there. Now, if the switch is closed, the electrons will move, the charges will move around that circle around there in the circuit. And then V this time will measure, let's say 2.6 volts. And then the V is measuring the potential difference. Why? We said the battery has its own internal resistance. So there is 0.4 of lost volts, 0.4 lost volts. That is, we get from 3 volts minus 2.6, we remain with 3.4 volts. So you say 3 volts minus 2.6 is equal to 0.4, which can be seen as 3 volts is equal to 2.6 volts plus 0.4 volts. Now this we said is the EMF. This is the potential difference. And this will be the lost volts. Why the lost volts? It's because of the internal resistance. When the current passes there, because of the internal resistance, we'll have IR, I small r, which gives us the lost volts. Now let's go. We'll come back to that. There are only 5 things that you have a look at here. The rest are the derivatives. 1, we look at the definition of electric current, and it says that current is the rate of flow of charges that is I. What charges are flowing there? That's the rate of charges. That's that thematically. And the charges are measured in coulombs. And their time is measured in seconds. So a coulomb per second gives us the amperes. let's say coulomb per second, gives you the amperes. We use 8, the symbol there for current, S for seconds as the unit, and the unit for the charge is a coulomb. That's number one. And another definition is that of the potential difference. Potential difference is the amount of work done the amount of work done per charge, that is the potential difference, is work per charge. Work is measured in joule and the charge in coulomb, and the potential difference in volt. So 1 volt is equal to 1 joule per coulomb. We have the third one, which is Ohm's law. Ohm's law the resistance of a resistor is equal to the potential difference divided by the current that passes there. This tells us that V is directly proportional to the current on the resistor, and other factors are kept constant. That's what we have. We are going to have a look at combinations so that you can go to the third, the fourth, and the fifth. This is resistor 1. That's resistor 2. As the current comes in here, you will appreciate that some will go that way, some will go this way, and you can say I1 there, second current there, and when it comes here, the whole current, total current, that is I1 plus I2, meaning that I1 comes this way, I2, they meet to make the I total there, which is I1 plus I2. Now, these resistors are in parallel. This is a parallel combination of resistors in that circuit. So you can see that there is the current is being divided by the resistors in parallel. If your voltmeter here measured, let's say 3 volts, if your voltmeter measured 3 volts here, Now, when the switch is closed, the current moves by, current divided there, we say resistors in parallel are current dividers. While the potential difference is the same across them. Now, what it means here is that if we put a voltmeter here, this voltmeter will measure 3 volts. If we put another one that side, this will also measure 3 volts. Now let's take the combination that is in series. Before we go there, let's finish up what will be the total resistance, what you call equivalent resistance. The equivalent resistance of the parallel combination will be 1 over R parallel. And this will equal to 1 over R1 plus 1 over R2. Now these are fractions. These are fractions. Note, if R1 is equal to 5 volts and R 5 ohms, not 5 volts, R is measured in ohms, and R2 measures 2 ohms. The total equivalent or equivalent resistance of the parallel combination must be less than the smallest, and the smallest is 2 ohms. In your calculation here, if your parallel combination is equal to or greater than 2 ohms, you need to have a look at your calculation, something wrong there. Always, the equivalent resistance of a parallel combination will be less than 2 ohms. You can do your arithmetic there. Now, let's switch to the series connection. A series combination here R1, R2, R3. Now, the total resistance of a series combination will be R1, R2, and R3. That's what you have. Basically, you see is the sum. If here I had 2 ohms, and here I had 4 ohms or 3 ohms, if I have 4.3 ohms, 3.3 ohms here, and here I had 6 ohms, I had to add them up. that will be 2 plus 3,3 plus 6 ohms. This is 11.3 ohms. Now, look what happens. When the current comes, it will flow in there, go there, go there, go there. Now, if we had let's say we had 24 volts here. The voltmeter measures 24 volts. And the resistance of R1 is equal to, no, it's not equal to that of R2, and it's not equal to that of R3. These are not identical. These are not identical. If the resistors were identical, they were to share 24 volts, that would mean 8 volts here, 8 volts here, 8 volts here. Now they are not identical. Therefore, they will have different voltage. Let's say this one has 12 volts, and this one here have 8 volts, and this one here will have 4 volts. Now, we simply say resistors in series are the potential dividers. Potential dividers, while the current is the same through them. The current is the same through the resistors. If you add the potential difference here and on the second resistor to the last resistor, you'll end up with 24 volts. You'll end up with 24 volts. That gives you the total potential difference from the source there, which was 24 volts. Now, let's go back to the previous page and see what we have. The first one I said is the flow of charges. We know that charges which are flowing here are electrons. Charges which are flowing here are electrons. But we also have what you call a conventional current, which you expect to move from positive to negative of a battery, from positive to negative. This is called conventional current. The scientists sat down and they agreed upon this, but in reality, we know that only the electrons are flowing So in reality, the charges will flow from negative to positive. In real world, only electrons are flowing. These are electrons, but conventional current is that. Now, the current is the rate of flow. How many charges are flowing there per second will define the current for you, give you the size of the current, the magnitude of the current. And the potential difference is the amount of work that the battery or the cell can do on charges to make the charges flow. Let's go back to. Now, if you have your battery here, the strength that the battery can do on the charges to make the charges to move around, work done on the charges, define their potential difference. Now that's what we have. And then the work is measured in joules in honor of a scientist called Mr. Joule. And then the third one is Ohm's law, which says that the potential difference is directly proportional to the current, or the current is directly proportional to the potential, meaning that if the voltage goes up, the current will go up. That's a direct proportion. Inverse proportion, one will go down, other one will go up. This one is a direct proportion, Ohm's law. Now, if you look at the three, you have V here. You also have V up there. You have I here. You also have I up there. So you can sharpshoot for either one of them, depending on your given data when you are given a question. Then here, we go to number 4, and that will be our number 5. We have resistors that are in parallel. Now, for this parallel combination, the current will be divided. Some of the water will go up, some of the current comes here, that will meet up there. We say resistors in parallel are current dividers, while the potential difference is the same across them. Now, potential difference, I said, is 3 volts here and 3 volts there. Please don't add them up to give you 6. Doesn't work that way. It only works on the series combination. So the potential difference will be the same across those resistors. Coming back to your series combination, the current goes through there, goes through there, goes through there, goes that way. Now, you have the resistors in series, which are the potential dividers, while the current is the same through them, meaning that if you have an emitter here, an emitter measures 2 amps, it means here we will have a current of 2 amps passing by here. We will have 2 amps passing here. We will have 2 amps passing there. Current is the same. Current is the same through those resistors. That's what we will have. While the potential difference is shared among the resistors there. And if the resistors are identical, they will share equally, they will divide equally. Meaning, if R1 was identical to R2, the same as to R1, they will share 8 each. 8 by 3 will give you 24. They shall divide 24 by 3 to get 8 volts, 8 volts, 8 volts. They simply don't have 8 volts simply because they are not identical. The one is 2, the one is 3.2, the other one is 6 ohms. We shall meet in the next lecture where we will look at problems based on circuits and how we jiggle around with those equations and definitions to maneuver our way on the circuits. That will be enough for today.